Hello. This will be a demonstration of proposition 20 from book 7 of Euclid's Elements, which says that the least numbers of those which have the same ratio with them measure the numbers which have the same ratio, the same number of times, the greater, and the less, the less. It's a confusing enunciation. We have a new idea in here, least ratio, which we never found with magnitudes, and in fact can't find with magnitudes. We're going to take our time with this proposition because we need to develop this idea. It's a very important idea. Okay, so we're going to have two numbers, CD and EF, and they will be the least numbers which have the same ratio with A and B. An example of this would be that 2 and 3 are the least numbers which have that given ratio of 2 to 3. They're not the only numbers with that ratio, like 4 to 6, 6 to 9 all have that ratio, but 2 and 3 are the least numbers which have that same ratio. So given that the ratio of CD and EF is the least of that ratio, then what we're going to prove is that CD measures the number A the same number of times that the number EF measures the number B. In other words, that they are equal parts. So CD is the same part of the number A that the number EF is of the number B. Now, if this is not the case, then CD has to be parts of A. If it is not a part of A, it is therefore parts. That's simply by a proposition 7.4. Okay, so if the number CD is not a part of the number A, then it has to be parts of the number A, which then also means that the number EF is the same parts of B that the number CD is of A. We get this from the fact that our given tells us that CD is to EF just as A is to B, which means by proposition 7.13, if we alternate this proportion, we can then say that CD is to A just as EF is to B by the definition of proportionality, which is definition 7.20. Whatever part or parts CD is of A, the same part or parts EF is of B. Now, we set out in our first step that because CD is not a part of A, it has to be parts. So CD is the same parts of A that EF is of B. Which means then that because CD is parts of A, we can cut CD at some points such that the segments we get are each a part of A. So we're going to do exactly that. We're going to make the two numbers here, 2 in this case, because it's the smallest of non-trivial case, but we can do 3 or 4 parts. But we're just going to deal with 2. So we're going to have the numbers CG and GD both be a singular part of A. And likewise, we're going to have the two numbers EH and HF each be a singular part of the number B. And we notice we're going to have the same multitude of them because CD is the same parts of A that EF is of B. So we're going to have two parts within CD, each of which are the same part of A. And likewise, within EF, we're going to have two parts, each of which is the same part of the number B. Now, the number CD being equal to the number D and the number EF being equal to the number HF, this is simply by virtue of our third step here, what we just did. It then follows that the ratio that CD has to EH is the same ratio that GD has to EF, right? Because CD is equal to GD and EH is equal to HF. CD is going to have to EH, the same ratio that GD is going to have to HF, which then means by proposition 7.14, that is one of the antecedents is to one of the consequents. So the sum of the antecedents is to the sum of the consequence. Because CD is to EH, just as GD is to HF, then follows that CG is to EH also just as CG plus GD is to EH plus HF. Now, CD plus GD is obviously the number CD, and EH plus HF is just the number EF, so that we can say that CD is to EH just as, or CG is to EH just as CD is to EF. So these two numbers here, CD and EF, have the same ratio as CD and EF. Now it's also obvious by common notion 5 that CG is less than CD and EH is less than EF. But they also have the same ratio as them. But we had said in our given that CD and EF are the least numbers which have that same ratio. But here we have just found CG and EH, which are lesser numbers than CD and EF and still maintaining the same ratio. So that being our given, that CD and EF are the least numbers with that same ratio, CG has to be greater than CD because if it's less, it violates our given. But if it's greater, that obviously violates common notion 5, right? Because CG is obviously a part of CD. So we have it now at our sixth step that CG is simultaneously greater than and less than CD. This is manifestly absurd, and so we can say that CD is not part of A, which then means that it is a singular part of A. And again, because of our second step here, we know that CD is to A just as EF is to B, which means that by the definition of proportionality, whatever part the first is of the second, the third shall be of the fourth. So we can say because CD is a singular part of A and CD is to A just as EF is to B, then it follows that CD measures the number A, CD is the same part of the number A, that EF is of B. So CD measures the number A the same number of times that the number EF measures the number B. And this is precisely what we set out to prove, which means we are done with the proposition, therefore, etc. QED. Again, because least ratio is like a new concept that we're seeing with numbers, it's kind of hard to understand unless you have an example. So let's go through an example. If we have some ratio, let's say 4 to 6, what are the least numbers that have this same ratio? Well, it's obviously 2 and 3. These are this is the least ratio. These are that 2 and 3 are the least numbers, which have the same ratio as 4 and 6. What we would call this nowadays in like elementary mathematics is putting a fraction into simplest terms. If we were to put this fraction 4 to 6 here in simplest terms, we would get 2 to 3. And these are obviously the same ratio, right? 4 is to 6 just as 2 is to 3. And what we're proving from this is that 2 measures 4 the same number of times that 3 measures 6. That 2 measures 4 the same number of times that 3 measures 6. Another way to write this, of course, with modern notation, is that 2 is to 4 just as 3 is to 6. And this is different from like 3 being to 4 just as 6 is to 8, because 2 is a part of 4, not parts. So 2 is the same part of 4 that 3 is of 6. This concept of least ratio is going to be very important for how, just for the rest of Euclidean number theory. So it is important to get it down and just remember it as just an ancient way of what we now say is the simplest terms of a ratio, of a fraction. That's all I've got to say about this proposition, so I'll end the video here and move on to 721.